Yeah, we still don't hear you. Maybe some technical issues with the with the microphone.
Hello, hello. Can you hear
Yes,
me?
now.
Yes,
Okay.
we can hear you now.
Okay, thanks. So as a heads up, my background is not really in stochastic thermodynamics so much. I'm more from the quantum information community. And I will actually talk about work that's a few years old already. And it's quite related to what Artemi was talking about yesterday. And I actually had some fun revisiting this old work, and I think it's actually still relevant. So I hope that you also find it, at least some of it, interesting. So I will talk about the effect of control restrictions in quantum thermodynamics. And the basic motivation is the one that we've heard of many times already in this workshop. So if we have macroscopic machines, then thermodynamics is very useful because on the one hand, it tells us what kind of bounds are there to the efficiency, say, of such machines. But not only that, we also learn that to actually achieve these bounds, we don't have to control the systems very precisely. It's sufficient to actually control these macroscopic properties of the systems. We don't really have to control each microscopic molecule of a gas in the piston. And in the recent years, many works have shown that for quantum machines or even other microscopic machines, say, at least in principle, they're also under the right circumstances are some sort of thermodynamic laws, which are then often formulated in, say, relative entropy measures and so on. But I think it's less clear what the implications are once you have limited control over the systems and how sensitive the results are to limited control of the systems. So that's what I want to talk about today. And I want to do this in a very simplified and idealized setup that I think still gives some interesting insight. So what we'll consider is that we have some quantum system here indicated by these two spins and described by some Hamiltonian that's time dependent. And we imagine that we can essentially do three things. One is we can just change the Hamiltonian over time. So we drive the system. The system evolves unitarily. And then this is associated with some average work cost or gain. And the other thing we can do is that we can couple the system to one of two baths, either a hot one or a cold one. And then when we leave the system coupled to one of the baths, then the system thermalizes. And then we can alternate between these sort of elementary operations in arbitrary cycles. Cyclic meaning that the Hamiltonian in the end has to go back to its initial value. Now it's clear that this doesn't yet fully specify a physical model, and there's a whole landscape of assumptions that one can explore here. For example, you can talk about whether the coupling to the environment can be controlled to some extent or whether it's sort of given by nature. You can discuss about whether it's weak or strong, this coupling. You talk about whether you can implement arbitrary Hamiltonians on this system or not. Or you can also, and this is a fairly recent topic, talk about heat baths that actually don't thermalize in the sense of statistical mechanics. For example, you could have many-body localized systems, or more generally, many-body systems that thermalize to so-called generalized Gibbs ensembles. Today I want to talk about points 1 and 2, and in particular how these 2 points are actually interrelated. And we have general result in all of these settings, but I want to mostly focus on very simple toy examples here today. Okay, so speaking of toy examples, let me just illustrate this framework. Okay, before I come to that though, we should sort of agree that the weak coupling limit in this sort of model, class of models, really consists of the following assumptions, namely that once you couple the system to one of the baths, then the work cost of coupling can be neglected. Second, that if the system thermalizes, it actually thermalizes to the Gibbs state of its instantaneous Hamiltonian. And third, there's a amount of heat transferred from the system to the bath or vice versa in this thermalization process. And this, in many circumstances, can just be then calculated at this expected change of energy. Okay, so let's illustrate this framework. So assume, for example, that we have a two-level system. And for now, let's stick with one heat bath to talk about work extraction instead of cyclic engines. And then if your initial state is diagonal in the energy eigenbasis, one can show that it's actually always beneficial to stay in this eigenbasis. Even though you can in principle implement arbitrary unit transformations in this adiabatic part of these protocols, it's not useful to do this. And then we can really restrict to a classical description or semi-classical description. And then what we are left with is this excitation probability of the two-level system and the energy gap of the Hamiltonian, which is delta. And then we have a two-dimensional phase space, essentially. I've indicated here this isothermal, meaning the probability or the excitation probability at the bath's temperature, and the yellow dot is just some initial condition. And now when we want to extract work, what we do is, at least in the optimal protocol, we first increase the energy gap, and then in many small steps, we alternate between changing the gap and thermalizing to walk along this isothermal back to the initial Hamiltonian, and we extract a certain amount of work. And such protocol really exists for any initial quantum state in any Hamiltonian. And many people have observed independently that the maximum amount of work that you can extract in such a manner is given by this quantum relative entropy expression that I've written here. You can also write this in terms of non-equilibrium free energies if you want. So what I want to discuss now is what happens if you actually cannot change your Hamiltonian arbitrarily. And to really illustrate this with a very simple example, let's consider the case where for some reason you cannot increase this energy gap of your two-level systems beyond some critical strength. Then in this adiabatic part, you can still do any unitary transformation on your system. It's still not useful to actually do this if you start in the energy eigenbasis. So consider the case where you have some initial condition now, and you're already at this border with your initial Hamiltonian. Then there are essentially two things you could do in the first step of your protocol. You would either thermalize, in which case you haven't extracted any work and you're stuck essentially, or you could go to the left and then at some point thermalize and go back to the initial Hamiltonian. And in both cases, you would at most extract negative work. So it turns out that really you cannot extract any work, any positive work, because you cannot essentially perform any counterclockwise cycle in this diagram. And that means that this initial configuration is really passive, simply due to the fact that you have limited control over your Hamiltonian. And the basic reason is that you cannot cross the isothermal in this diagram in the vertical direction. You can only go to the isothermal. So you might ask, okay, is there any way we can maybe circumvent this problem? Is there any way we can gain work from the system, even though we cannot increase the Hamiltonian's gap over this critical value? And turns out that you can, if you assume that you have more control over the coupling to the heat bath here. And to do this, I will now present a simple quantum channel that you could implement in principle. So this is a completely positive trace preserving map in the quantum case, or just a stochastic matrix in the classical case. And this has the property, this particular one, that you can implement it by coupling your system to a single harmonic thermal harmonic oscillator, or to a bath consisting of a few thermal bits using an energy preserving unitary. So this would be a very small bath. And if you can make use of the bath, you can implement this dynamics. And this dynamics has the property that it leaves the thermal state invariant. And this implies that you cannot use such dynamics to actually violate this bound about the maximum work extraction that I put in the beginning. However, this channel lets you do something quite peculiar, namely it induces an approximate population inversion. So when you would start in the ground state of your Hamiltonian, then it would actually map you to a probability distribution above the isothermal. And now when we go back to our example and we use this as the first step in our protocol, so we couple to the heat bath in a very peculiar way, then we can jump over the isothermal, so to say, and now we can decrease the gap and come back and extract positive work. So this means that the increased control over the system-bath interaction can lift the restrictions imposed by the lack of control over the possible Hamiltonians. Okay, so maybe we can also look, okay, actually before I come to that, maybe some comments on this funny interaction with the bath that I talked about. This is now called the beta swap in quantum information related literature. And it has the very interesting property that if you're in a classical setting, then this cannot be implemented by Markovian evolution. This might not be surprising because actually you can imagine that if you go up here, you just, so if you go up here, you just get stuck on this isothermal line. However, in the quantum setting, you can implement this evolution in a Markovian way. In fact, this has very recently been explored by Kotsekwa and Matthias Lustaglio in this recent preprint, and I invite you to read this preprint if you want to know more about these processes. Okay, so maybe this lack of control that I described in terms of this energy gap is not so relevant. So we can also ask about local control, for example. So now we imagine we have some set of spins, and these spins interact via some fixed interaction here. And we cannot change this interaction, but we can change the on-site magnetic fields here. And then it's a general result in quantum control theory that with this possibility, you can still implement any unitary on the full system, provided that this interaction is sufficiently generic. So you have huge control over your system in a sense. Right? You can run a quantum computation if you want. Again, you can ask, okay, what's the thermodynamics of this? And we proved some years ago that if we consider this in the setting of just 2 qubits, then again, you can have initial out of equilibrium distributions for the initial Hamiltonian, which is just the sigma z tend to sigma z, so like an Ising interaction, namely the mixed initial state that is still passive. You cannot extract any work from this. And again, there exists such a special quantum channel that allows you to extract work. And it's again preserving the thermal state. And I will not present the proof, it's quite complicated, but it's a very similar result to what we've seen before. Now you can ask, okay, what about even more complicated settings? What if you have a many-body system, say? And for this, I would like to discuss really the case of a cyclic heat engine. So we now consider the setting of 2 heat baths. So we have a hot bath and we have a cold bath. And we want to perform a cyclic protocol. And then you can prove a general result about the efficiency that you can achieve under arbitrary sets of Hamiltonians that you could in principle implement. It looks like this with these expressions. I don't want to go into details. Basically, it's an expression that one has to optimize over the unitaries that can be implemented under the given control and over the possible Hamiltonians one could choose. But I want to present the results that we get in a case study where we use this result. So, and this will actually be a pretty much classical setting. Namely, I want to discuss the one-dimensional classical Ising model. And now we assume a very particular form of control that you have, namely that you can just change the on-site magnetic field in a homogeneous way throughout the full spin chain. And we're interested in figuring out how the efficiency of the machine built from such a spin chain might depend on the interaction strength between the spins. So it's a function of the spins, of the interaction strength. And what we find using our general result is the following graph for the efficiency at maximum work density, which essentially also corresponds to the maximum efficiency here. And looks like this. So on the left, in the antiferromagnetic regime, you can reach Carnot efficiency with extracting finite work per particle from the system in a per cycle. then in the strongly ferromagnetic regime, you can actually prove that the efficiency has to vanish, and the work per particle also vanishes as the interaction strength diverges. And then there's this funny critical point here for the interaction strength, and you see this sort of kink behavior, which is reminiscent of a phase transition, really. So what happens at this point is that the optimal protocol you need to implement in your cycle changes in a non-analytic way. And this is true in the thermodynamic limit, of course. For finite systems, you don't see this behavior so strongly. But there's actually quite an interesting story behind this graph. Unfortunately, I don't have time to explore this in detail. But you see that we find a very asymmetric behavior depending on whether you have strongly antiferromagnetic systems or a strongly ferromagnetic system. Okay, so with this, I actually also already want to summarize. So what we've seen is that if you have limitations on the implementable Hamiltonians on your system, then this can lead to situations where you can extract zero work from non-equilibrium condition. And this is very similar to what Artemi showed yesterday with the Szilard engine, where you cannot access this vertical horizontal split, but only you cannot access a vertical split, but you could access a horizontal split of the box, so to say. And this is even true if, in principle, you could still be able to perform arbitrary unitary dynamics on your system by this restricted class of Hamiltonians that you can access. We've also seen that these limitations may be overcome to some extent, at least sometimes in these toy examples that I gave, if you have access to small heat baths that you can control well, in the sense that you can perform unitary energy preserving dynamics on the joint system. And the most extreme case, we saw that actually a single thermal harmonic oscillator is sufficient. And what I didn't talk today is things. So we also looked in strong coupling settings and heat paths that thermalize to generalized Gibbs ensembles. And there you can find somewhat related effects. And maybe some open problems in this direction that we've already heard about before, actually. So I think it would be an interesting open problem to study, instead of how mean values, say energy, work, and so on, are constrained by these control restrictions, but how fluctuations depend on these control restrictions, right? You could imagine that a small system might want to optimize fluctuations instead of efficiencies in the first place. And second, I think it will be interesting to more systematically study how locality constraints arise or modify the thermodynamic behavior, like in the example that I gave, where you have only local control over a system. And that's all. Thank you all very much. And thanks a lot for organizing this super nice workshop. I'm enjoying it a lot. And here you have some references if you're interested in. Thank you.